So today's speaker is Johan Öinert, and his talk is about, well, the title you see there, Primeness of group-graded rings with applications to partial cross products and Leavitt path algebras. Please, Johan.
Thank you very much. So I will start by thanking the organizers, Guillermo and Gisela, for inviting me and giving me the opportunity to give a talk here today. Yes, the topic of this talk is about Primeness, and I will go directly to the first slide if I can. Oh, this doesn't look so good on my screen, but let's see what happens. So this is a joint work with the three Swedish colleagues, Daniel Lännström, my former PhD student, Patrik Lundström, a long-time collaborator, and Stefan Wagner, who is a senior colleague at the Blekinge Institute of Technology, where I also work. Yeah, so the outline of this talk is that I will give you some background, so some motivation for this study that we have conducted, some background about results on group rings, some generalizations for strongly group-graded rings, and then some more recent results about Leavitt path algebras. And then I will tell you about the very fairly general class of group-graded rings that we call nearly epsilon-strongly graded rings. And then we have a main result, which builds upon previous results for strongly group-graded rings. Not a very beautiful result, perhaps, but it turns out to be quite useful. The proof is complicated, so I will not go into any details there, but I will make some comments about the proof, and then at the end here I will explain how one can apply this main result to get some new results for Primeness for these three types of rings: Leavitt path algebras, partial cross products, and something that we call S-unital group rings. Nothing happens. So in 1963, Connell proved this result, giving exact conditions on when a group ring over a unital ring is prime. So it turns out that this happens exactly when the coefficient ring, big R, is prime and the group itself has no non-trivial finite normal subgroups.
Johan,
yes?
Could you, I always get confused between the distinction of prime and primitive and all that. So could you simply spell out your definition of prime ring?
Yes. So how does my screen sharing look to you? Is it double layers of things?
We see something in the bottom related to the first slide, but it doesn't really disturb us too much. So you can perfectly go on like that.
Yeah. Okay. Let me try to.
It's just the first page that was left there for no particular reason.
Is it possible maybe if I stop sharing and then make full screen and then share? Is that the order?
Okay, great, fine.
How does it look now? Can you see my?
Yeah. Now we see just one screen, one page.
Okay, so I will try to see if I can write here. or maybe I could just say it. So what I mean by prime here is that if you have two non-zero ideals, their product should not be zero. So this is what I mean by prime.
Okay, thank you.
All right, so this is a result by Connell from the 1960s. And then, so the group ring is, of course, well, this is an example of what we call a group graded ring. So I will, now it happened again.
Don't worry, we can live with that. It's not terrible.
Maybe I shouldn't use full screen. Maybe this is the problem.
Johan, this is really not disturbing us at all. You can clearly go on like that, and we can see it as well as if there was no problem. Okay, that's good to hear. It is a little bit problem to me because when I click, nothing happens. So if you
okay,
if you don't mind, I think I'll keep it like
okay, fine.
It's under control.
Fine.
Okay, so let me just recall the definition of a group graded ring. So we have a group, big G, and then we have a ring S, and then we have these additive subgroups SG, such that we can write the group as a direct sum of these additive subgroups. And the product in the ring is compatible with the group multiplication in the sense that when we multiply homogeneous elements from these components, they end up in the corresponding component labeled by GH. So that is the definition of a G-graded ring. And I should also say that you can do this for unital rings, for non-unital rings. And also these component SG, they can be zero. So everything is possible here. So, and we have a bunch of examples. Of course, I mentioned the group rings. You can take a matrix ring and you can grade it by, you can take a finite a ring of n by n matrices and grade it by, for example, the additive group of integers. You can grade it by the cyclic group of order n. And in general, there are many different ways to put a grading by one group or by different groups on a particular ring. So when I talk about that S is a G-graded ring, I mean that we sort of fix a grading on that ring and then we work with that grading. But in general, you can do this in many different ways. So if we specialize the definition of a G-graded ring and require not only that we have inclusion here, but that we have equality, then we call it the strongly G-graded ring. And the group ring with its canonical grading is one example of a strongly G-graded ring. So what Donald Passman did in the 1980s is that he tried to generalize the result by Connell into the setting of going from groups to more general cross products, algebraic cross products. And then at some point, I think he realized that what he was doing there could actually be generalized to strongly group graded rings in general. So he obtained this result. So there's some notation here that I will try to explain. A unital and strongly G-graded ring S turns out to be not prime if and only if all of these three conditions are satisfied together. So there should exist a finite, first of all, there should exist two subgroups N and H of the group G. And this group N should be finite and it should be normal in the other subgroup H. And then I guess I have to explain the notation a little bit. So whenever you have a subgroup big N of a group big G that grades a ring S, then you can look at this restriction. So you just take the components that are labeled by elements from the group N, and then you take the direct sum of those. That will give you a subring of your ring S. And we also have this notation here. So we take any subset, you can do this with any subset big I, and then you take these components from the grading, S, X inverse, and SX, and then you conjugate in this way. That is the I raised to the power of X. This is what this means. So we basically just take the subset and conjugate it. And for a certain subset, you can talk about invariance. So for example, if you have, like here, you have an ideal in SE, then you can actually conjugate it like this, and you get a new ideal in SE. And then we just, when we talk about, for example, H invariance, what we mean here is that this ideal I, when we conjugate it like this, with any element coming from the group big H, we should end up inside I again. So this is what we mean by H invariant in this theorem. And the other requirement here is that this product should always be 0 when we take an X that sits in the complement to big H. All right. And then the third condition is that there should exist ideals, A tilde and B tilde inside this subring. There are ideals in this ring, and they should also be H invariant with respect to this action that I describe here. And moreover, they should sit inside this subset. So this I here is the same I that appeared up here. And also their product should be 0. So, I mean, many things working together here. It looks a little bit, maybe not so nice, but this turns out to be the characterization for strongly grouped graded rings. So we will use this notation later on, so I advise you to keep this in mind. Okay, so Leavitt path algebras. I'm not sure. I gave a similar talk in Brussels a month ago, and the crowd there was not so accustomed to Leavitt path algebras. But maybe I don't have to talk about the history here, but I just mention that anyone who likes to learn to know more about Leavitt path algebras should look up this very nice article by Gene Abrams from 2015, where he describes the development of the field in the first 10 years since their introduction in 2005. So there is a result for Leavitt path algebras that I also want to mention, but before that, I remind you of the definition. So we have here a directed graph E consisting of a vertex set E0 and an edge set E1. And then we have a unital ring, not necessarily commutative. In the original definition, it was a field, but you can do this for any unital ring. So the Leavitt path algebra with coefficients in R, we just define it as the free associative R algebras. We take as generators, we take all the edges, all the vertices of the graph, and we also take these symbols F star, which are commonly referred to as ghost edges. And this is our generators. We generate an R algebra where we let the coefficients commute with the generators, and we do this subject to these 4 relations. So the vertices are orthogonal idempotents in the algebra. So I guess it's not explained here, but S of F is the source of the edge F. R of F is the range of the F, the edge F. So they should satisfy certain relations here. All right, so what you can do here is that you can equip this Leavitt path algebra with various gradings, but the most commonly studied is probably the Z grading. So you take the additive group of integers, and then you just prescribe that you want it to have a certain grading by assigning degrees. So you say that for every vertex V, the degree should be 0. For every edge F, the degree should be 1. And for every so-called ghost edge, the degree should be -1. It's freely generated algebras. You can do this by just assigning degrees to the generators. The only thing you have to keep in mind is to make sure that these assignments are compatible with the relations that you mod out by. So it should make these relations
Johan,
homogeneous. Yeah, sorry.
I mean, normally an R algebra is a bimodule over the ring when the ring is commutative. And so, I mean, normally an R algebra is a vector space over R. So are you requiring, I mean, I'm wondering about what's the definition of an R algebra when R is non-commutative? It should be postulated to be a bimodule over R?
But R is he assumes that R is unitary. So there is a homomorphism, and that's it. There is a homomorphism from R to the Leavitt path algebra that is unitary, and that makes it into an algebra with R.
Okay, that makes it simple.
That's one way of putting it, yeah.
Otherwise, if R is non-unitary, you simply define this over the integers and tensor with R, and that's it.
Okay. Thank you, Guillermo.
Yeah, thank you. Yeah, so we have this grading. I mean, you could do this with other groups as well, but this is, I think, the most accessible and interesting grading in general. All right, so this means that we can try to study this Leavitt path algebras from the perspective of graded rings, and this is also something that we will do. So before I continue, I should also just, as a side note, remark that there are other gradings on Leavitt path algebra. So if you're working over a field, you have a directed graph, then you can show, it was shown by Gonsalves and Royer, that the Leavitt path algebra is actually isomorphic to a certain partial skew group algebra, where the group acting is the group generated by the set of edges of the graph. So these type of objects, partial cross products or partial skew group rings, are naturally graded by the group acting. So here we actually have another grading. So this gives you another grading on the Leavitt path algebra by the free group generated by the set of edges. This is not something that I will use today, but I just wanted to mention this. Okay, so in order to describe primeness of Leavitt path algebras, we need this definition of the so-called condition MT3. So that condition is requiring that for any two vertices that you choose in your graph, there should exist a certain vertex such that you can go from, such that you can take paths from the first two vertices and have them meet in the last vertex W. So you take U and you take V, there should exist some W such that you can go with paths from U to W and from V to W. So this is called condition MT3. And then I didn't write it up here, but there was a previous result, previous to the one that is on the screen here, by Abrams-Bell-Rangaswamy, where they proved this in the case when R is a field. But then Larki, a few years ago, generalized this to the case of R being a unital commutative ring. So it turns out that the Leavitt path algebra over this unital commutative ring is prime if and only if the ring R is prime and the graph satisfies this condition MT3 mentioned above. So I can just say that this proof of Larki doesn't seem to use any graded techniques as far as I can tell. But we will show later on here how this can be generalized to using graded techniques and using our results. Okay, so now we come to part 2 here. So if we have a G-graded ring, then we say that this is symmetrically G-graded if it satisfies this condition. So we take component SG, SG inverse SG, then this should be not only included in SG, but it should be equal to SG for every G in G. And I think that the definition of the symmetrically G-graded rings appeared first in a paper by Rui Excel and his co-authors some years ago. So this is a relatively recent concept, I think, and not that well studied. But it's an interesting class of rings. So an observation before we continue is that if you have a unital and strongly G-graded ring, then first of all, it has to be symmetrically G-graded. So if you remember the definition of strongly G-graded ring, you could see directly that the left-hand side here just has to be equal to SG from the strong grading. So a strongly G-graded ring is always symmetrically G-graded. And if it's also unital, then if you form this product here by the component SG times SG inverse, so this is a ring in itself. You can easily check. I mean, in general, not only for strongly group graded rings, this is always a ring. But in this particular case, it is also a unital ring. And why is that? Well, for strongly graded rings, this is actually equal to, this product is equal to SE. And if you have a unital group graded ring, not necessarily strongly graded, but just in general, the multiplicative identity element of the ring is always sitting inside this component. So maybe I should say that E here is the identity element of the group. Were there any questions in the room? No? So this is just an observation. A unital strong G-graded ring is always, the grading is always symmetrical, and this subring here is always a unital ring. So this leads us into the first definition to understand the notions here. Something that we call an epsilon strongly G-graded ring. So we have a G-graded ring S, and then we say that it's epsilon strongly G-graded if it is symmetrically G-graded, and every such subring is a unital ring. So for every G, it should be unital. So I mean, from the previous slide, we see that, yeah, this is always satisfied for unital strongly group graded rings. So this is a generalization of unital strongly graded G-graded rings. So the remark I want to make here is that these rings are always unital. It's maybe not completely obvious just by looking at the definition, but it turns out that they are always unital. So the examples here, apart from the obvious one that I just mentioned, unital strongly G-graded rings, are Z-graded Leavitt path algebras with the grading that I described before, but not in general. It turns out that it's only the case when E is a finite graph. So when the graph is finite in the sense that the vertex set and the edge set are both finite, then it turns out that the Z grading on the Leavitt path algebra is of this type. But for a general graph, it doesn't have to be. And then if we take a unital partial action and on some ring, and we form the corresponding cross product, then this is canonically graded by the group G, and it turns out that grading is always. All right, so this is a special case of what I want to talk about. I'm moving into more general direction here.
Johan,
may I ask a little question?
Go ahead, Guillermo.
Yes.
When you say that the rings that are epsilon strongly G-graded are always unital, do you mean that the unit of SG inverse is always the unit of the ring for all G?
No.
Or is it a different idempotent?
No. So yeah, I mean, I have to be a little bit careful here, but when I say like this, I mean that this viewed as a ring in itself is a unital ring. But that doesn't mean that it has to be coincide with the unit of the whole ring. No. If that was your question.
No, I don't mean that you impose that as in the definition of unital. I mean that you say they turn out to be unitary, but not because, but the unit doesn't turn out to be the unit of the whole ring, the unit of SGG minus. That's what I was
saying. The unit that we get, the multiplicative identity we get on the whole ring actually turns out to be the multiplicative identity when you take, you replace the group element G by the identity element of the group. So you just have SE, SE. So it turns out to be the identity element or the multiplicative identity element of that subring.
Okay, thanks.
But if you just take a general group element G that is different from the identity in the group, then you get, I mean, it could be completely different unit element sitting in that ring. Yeah.
I also have a little question. So I understand that by SG inverse, or rather any product of sets, you always understand that as the abelian group generated by the individual products, right?
Say that one more time.
If you have two subsets of a ring, the product of the two subsets, I understand you can take the set of all products, but my impression is that you're actually referring to the set of all sums of products.
Yes, exactly. So I didn't clarify this, but this is sometimes called the module product, I guess.
Yes, okay, that's clear.
It's just like you said, we take sums of products, yeah.
Okay, so my question, so here in your assumption, you are requiring that there is an element that behaves as a unit for SG inverse, and that element will be a sum of products. Like any other element of that set. So my question is whether you require or whether you can deduce that this unit is a single product.
I think it is a single product because
if that is a single product,
because you know, if you think about, if you take G to be the identity of the group, then you will always have. Wait, maybe.
If G is the identity, you simply take the unit in SG, and the unit in SG times itself gives you the. Because I think that when if you can guarantee that the unit is a single product, then you quite likely can show that you are back into the third example that you described.
Yeah.
Do you have any example in mind which is not covered by the third example?
Are you talking about this one here?
Yeah.
That's a good question. I can't think of any now, actually. Maybe there are none.
Because I think that in my very first paper on partial cross products, the main result there is essentially proving that every epsilon-strongly G-graded ring is a partial cross product in a very special case of the integers.
Yeah.
Okay.
Well, that is perfectly possible. I mean, I know that there are some recent papers where some people have been trying to see when certain epsilon strongly graded rings, epsilon cross product, and so on can be realized as partial cross products. So there's some work going on there, but I'm not exactly up to date with the details. But so I don't want to get stuck here because I want to make this a little bit more general. And I can just say that this name is probably not optimal, epsilon strongly graded, but the idea here was that they are very close to being strongly graded. So I was not sure which audience I had today, so I just included the definition of an S-unitary ring here. So this is something that we will use here. So just recall that a ring is called S-unital if any element of the ring is contained in its intersection of these sets. Okay, so you can, then it can be shown, it was shown by Tominaga, that if you have an S-unital ring and you have a finite subset of that ring, then you can always find a so-called S-unit U here that works locally for this particular set as an identity element. This is very useful. So now we come to the definition of, in lack of better names, we decided to call it nearly epsilon-strongly graded rings. So it looks very much like the definition of an epsilon-strongly graded ring. The only difference is that we have replaced the unitality assumption on this subring, going from unital to S-unital. And it turns out that this accommodates a larger class of rings, of course. And now it turns out that, in fact, every Leavitt path algebra over any graph E, so it's not only the finite graphs, but any graph has a grading of this type. And of course, it includes all the previous examples that I mentioned. So, I mean, I guess it could look like we're just generalizing more and more, and what can we get out from this? But it actually turned out that this class of ring has some relevance to a notion called graded von Neumann regularity. So the notion of von Neumann regularity basically is asserting that any element of the ring A should be contained in A times the ring times A itself. And so this notion has been studied for a long time, but then I think sometime in the 1980s, it was also studied in the setting of graded rings. So there was a characterization of when a strongly graded ring is graded von Neumann regular. And you basically take the same assumption as in the von Neumann regular case, but you require it only to hold for homogeneous elements. The homogeneous element in the graded ring should be included in the product of itself with some element of the ring with itself. So there was a characterization for strongly graded rings. And then my PhD student, or my former PhD student, Daniel Lännström, in his thesis, he actually showed that he gave a characterization of when a general, not necessarily unital, not necessarily strongly graded ring is graded von Neumann regular. And it turns out that one of these necessary conditions is that the grading is nearly epsilon strongly graded. So it turns out in this context. Okay, so now I have talked enough to mention the main result, but before we go into that, there's another notion that we called non-degeneracy of the grading. So a G-graded ring is non-degenerately G-graded if for any non-zero homogeneous element S of degree G, we can always find some element in the opposite degree such that the product is non-zero from both left and right. So that turns out that this is a little bit more general than nearly epsilon strongly graded. So just take a look at here how the proof works of this necessity that a nearly epsilon strongly graded ring is always non-degenerately G-graded. We take an element S of degree G, and then we suppose that the product from one side is 0. And then we use here that it's nearly epsilon strongly graded. That means that the grading is symmetrical, which means that this homogeneous element S can be written as a sum of product like this, where AI and CI come from the same degree as S itself, and the middle element BI has the opposite degree. And then if we look at this finite set here, AI, BI up to A and Bn. So this is finite set. It is contained in big SG times big SG inverse, but by assumption that is an S-unital ring. So by this result by Tominaga, we can find some S unit that we call U for this set. And then we just do the calculation here. We can insert U. It turns out that we get an element, that the element S is contained in this product here, but by assumption, this right-hand side was 0. So the S has to be 0. And then you can do the same thing from the other side. But this is just in a minute, I will present the proof. So it's important to keep in mind that non-degenerate G-graded ring is weaker than nearly epsilon-strongly graded. Okay, so here is what our main result looks like. Yeah, I wish that it could be simplified more. It doesn't look that great, but it looks very much like Passman's result. So here we have a general group G, we have a G-graded ring big S, and then we have the same assumptions as Passman basically, with a little bit of difference that I will explain. So we have this A, B, and C, A being that S is not prime, B being the existence. So 1, 2, and 3 should be satisfied simultaneously here. The existence of this finite normal subgroup N in the group H, which is in its turn a subgroup of big G. And then there should exist H invariant ideal, big I, in the SE labeled by the identity element of the group. It should satisfy the same conditions as in Passman's theorem. The only difference here, which I would like to point out, is that we had to stick in this SH in the middle here. So in Passman's formulation of his theorem for strongly graded rings, this SH was not present. I will explain this in a minute, why that is the case. And then we have an equivalent version of B, which is word by word the same. The only difference is that we place the word H invariant here in front of ideals. These ideals, if they exist, they can be assumed to be H invariant. So the result itself is then that if we assume that the grading is non-degenerate, then this assertion C implies B, which implies A. But if in addition, we assume that the grading is nearly epsilon strong, then all three conditions A, B, and C are equivalent. All right. So maybe some comments about the proof here. So first of all, suppose that we have a non-degenerate G-graded ring and that there exist subgroups of the same type as in the theorem, and that we have this H invariant ideal I satisfying the conditions. So these conditions are the same as in the theorem. Then S is not prime. So this is one of the easy parts of the proof of the main theorem. So the idea here, I mean, it's a little bit, I've made it shorter. You can do this in maybe half a page or something like this. What you do here is that you take ideals, big A and big B, generated from the A tilde and B tilde given above. All right, so these are, of course, ideals in the bigger ring S. So there are two things that we need to show. Well, first of all, that they are non-zero. And second of all, that their product is 0. So keep in mind now that in the theorem here and also here, we're not making any assumption about unitality or anything like that. So we only have non-degeneracy. So if the ring S was unital, I mean, that would be obvious that A and B are non-zero, but we don't have anything like that. The only thing we have is non-degeneracy. But one can, in fact, use non-degeneracy of the grading to conclude that A and B are both non-zero. And then the part of the proof that actually requires a little bit more work here is to show that AB is 0. So the method of proof here is to look at arbitrary product like this. So we take A tilde with some homogeneous component SG times B tilde. We want to show that this is always 0. If we can do that, then it follows that A times B is 0. How do we do this? Well, we divide into two cases. So either G is contained in big H, the subgroup H, or it's contained in the complement of H. If it's contained in big H, then we have this assumption up here, guaranteeing that we will get a zero product here. And if instead G is contained in the complement of H, then we have a situation like in part 2 up here. Then we can actually use the invariance of I together with this property here to show that this product here will be zero. But that requires a little bit more work, but not too much. All right, so this is the easy direction going from B to A in the main theorem. And in order to keep track of these things, we introduce the notion of a so-called NP datum. We start with a G-graded ring S, and then we have this quintuple H, N, I, A tilde, B tilde, consisting of H, a subgroup of G, and N being a finite normal subgroup of H, and I being an H invariant ideal of SC satisfying these things. So it's the same kind of assumption that we had in the main theorem. But then there's a little bit of a difference here. So we have NP3 and NP4. In NP4, we have the same requirements as in the main theorem. Namely, you see here SH in the middle. Here we don't have that. So the SH is not here. So if we have that the SH can be placed in the middle and still get zero, then we call the NP datum balanced. All right, so what I will do now is that I will try to explain why for strongly graded rings, these two things are the same. Yeah, so first of all, for nearly epsilon strongly graded rings, the NP4 implies NP3. This has to do with S unitality. But the other one going from NP3 to NP4, yeah, so here we assume that the ring S, it could be of course unital, but we don't only need S unital, and that it's strongly graded. And then we suppose that we have an NP datum, and we want to show that it's balanced. So we just want to show that this product is zero whenever we take a group element little h from big H. So we assume here that the A tilde or the B tilde is H invariant, and then we do this calculation. So first of all, we plug in SE in front here. I mean, that's possible because the A tilde is an ideal in Sn, and I have to think a little bit. Yeah, so one can show that the S units has to sit inside this component here. So therefore, we get equality. And then in the next step, we use the strong gradedness. We replace SE by SH inverse. And then in the last step, we just use the fact that this is difficult to market, but this middle part here around the H tilde, this is this kind of conjugation that I mentioned in the beginning. And by invariance of A tilde, this is absorbed into A tilde. And then by assumption, this product was zero. And then you can do an analogous proof in the case when you assume that B tilde is H invariant. All right. Yeah, time is running here. What can I say? Yeah, basically we do the proof by splitting into two cases here. So we are working with the principal component SE being not prime, not G prime or prime. So maybe I should just say that G prime here, we mean that there are no, inside SE, there are no non-zero G invariant ideal whose product is zero together. And then you can do the proof like this. I think I will, yes, you basically have to check that it has this balanced NP datum. So in this particular case, I mean, the proof here basically shows how such a balanced NP datum could look like. You have these 5 things. For the group H, we just take the whole group. For the normal subgroup big N, we just take the trivial group. For the invariant ideal here, G invariant ideal I, we just take the principal component itself. And then we just keep this A tilde B tilde as our ideals whose product is 0. And then one can check that these MP1, MP2, and MP3 are satisfied, and also the balancedness one can show. So here one is using the non-degeneracy and the invariance and the definitions. I have to move on here. And then the hard part that is left is really the case when it's G semi-prime. So this requires long, spending something like 15 or maybe even 20 pages, including the preparations to actually prove this. It's very much based on Passman's ideas, but we adopt them to this nearly epsilon-strong setting. And it turns out that with a little bit of tweaking, the arguments can actually go through. So let me then mention the applications here. So in order to prove our results here for Leavitt path algebras, we need a couple of propositions. So the first one it gives us necessary and sufficient conditions for a graph not satisfying this condition MT3, and only the assumption that the coefficient ring R is prime. There is also a condition here giving us a situation where the graph does not satisfy condition MT3. And then the last proposition here, which is an adoption of an argument by Tom Ford from the case of I guess it was the case of fields, working over fields. So here we adopt this to unital rings and use an induction argument to show that if you have a non-zero element of degree 0, then there exists alpha and beta finite paths and a vertex V and a non-zero T in the ring, such that you can do this product and get out a non-zero coefficient in front of a vertex V. So using these two propositions and our main results, we can now prove this generalization of Larki's results, so going to a completely general, possibly non-commutative unital ring here, and show that the same conditions appear here. So the Leavitt path algebra is prime if and only if R is prime and the graph satisfies condition MT3. So 1 implies 2 is rather straightforward. Primeness of R is very straightforward, that E has to satisfy condition MT3, follows from one of the previous propositions. And then the proof going in the other direction, that R is prime and E satisfy conditions MT3 actually gives you primeness of the Leavitt path algebra is done like this. So if we suppose that big R, the coefficient ring, is prime and the Leavitt path algebra is not prime, then we want to show that the graph does not satisfy condition MT3. So what we use is that this observation that the Leavitt path algebra with its canonical grading is nearly epsilon strong. And then the main theorem says that there are non-zero ideals in S0. So why is that? Well, it's because what are the finite what is the argument? I lost it now, but yeah, so I guess it has to do with the fact that Z is torsion free here. So the N has to be the trivial group. So the A tilde B tilde is contained in S0. And this product is now 0. So here this SH appears, but in this case, it's actually SG. So the whole ring. And then we take some non-zero elements, A and B, in those ideals. And then we can use this proposition from the previous slide to get that there are elements, alpha, beta, gamma, delta, R and S, such that this holds. Then you form the product here. You can check that this product here is contained in this set. And that set is by the previous observations here, that set is 0. So this product on the left-hand side is 0. And then this, we should recognize this from the proposition from the previous slide. And using that and the fact that R is prime, we conclude that the graph cannot satisfy condition MT3. And that finishes the proof. Okay, I'm about to finish off. I will just briefly say that for unit of partial cross product, we could of course just copy the assumptions in all the assertions in the main theorem. It will look exactly the same with the standard grading for these cross products. In the case of a torsion-free group, we get a little bit nicer conditions here. So for torsion-free groups, it turns out that the corresponding cross product is prime if and only if the coefficient ring here R is G prime. And G prime is, I then define it in the sense that if you look at the action on these on sets of the coefficient ring, there should be no non-zero ideals whose product, non-zero invariant ideals whose product is zero. That is what I mean by G primeness for this R here. And then we have also the notion of an S-unital group ring. So we just define the group ring in the same way as the classical group ring, but we're no longer viewing the group elements as elements of the group ring because we're working over a possibly non-unital ring here. But of course, you can form a product in the same way. And yeah.
So you just tensor the ring with the group ring. You tensor R with Z or G.
Yeah, I guess that's one way of putting it. Yeah. And then we get the same conditions as in Connell's original result. So I'm not sure how useful this is, but it's some kind of application. I only briefly scratched on the surface of the proof of the main theorem here. If you want to learn more about this, you should look in our archive paper. Before I end, I just wish to point out the location of Blekinge Institute of Technology, which is one of the smallest universities in Sweden and probably in the world. So here you see Europe, and here you see Sweden. If we zoom in, here in the south of Sweden, here you have Copenhagen, here you have Stockholm. So if we zoom in even more, here you see the region called Blekinge, and then we have Karlshamn and Karlskrona, where we have the main campuses. So we're surrounded by the Baltic Sea. So out here, there was some gas pipes that were blown up recently, part of some probably connected to the war. So this is the region where we work in, and we are located, the math department is located in Karlskrona out here. And here you have a picture of our campus in Karlskrona by the Baltic Sea. So that's all I wanted to say, and thank you for your attention.
Thank you very much for a wonderful talk. I recognize Ystad there, the city where Wallander.
Wallander,
yeah.
He's here, yes.
Yeah. Okay, so I have two small questions. One is, I have some recollection, not very precise, that I think maybe there was some theorem that every Leavitt passage is for normal grading, or maybe one needed some hypothesis for that. I mean, how much in addition, so essentially, how much in addition to von Neumann gradiness do you need for your result on Primeness of Leavitt path algebras?
So let me just mention something. So just go back to this result by Lännström. So as I mentioned before, he gave a characterization, and the characterization is basically that a group-graded ring, not necessarily unitary. Group-graded ring is graded for Neumann regular if and only if the grading is nearly epsilon strong and this special subring SE labeled by the identity element of the group, if that subring is for Neumann regular. So using that result, so we go back in time some years ago, Rusby proved that if you work with Leavitt path algebra over a field, it is always for Neumann, graded for Neumann regular. This is what proved. So what Daniel proved is that as an application of this characterization that he came up with, as an application of that, as a corollary, he proved that Leavitt path algebra with the standard Z grading, I mean, it is always nearly epsilon strong. So this we knew from before. This means that the Leavitt path algebra over a unital ring is graded for Neumann regular if and only if the ring you're working over itself is Neumann regular. So of course, this is always satisfied for a field. So he, in that way, he generalized Rusby's Haskat's result. But that's just a little bit of context. You asked something about.
Yeah, later on when you have the applications, you have some application to Leavitt path algebras for the Primeness of Leavitt path algebras. And so since Leavitt path algebras are graded from Neumann, I thought maybe, I mean, this holds more generally for more general graded for Neumann rings.
No. So I mean, that's a really good question, but I think, where is it?
There is, but this is MT minus 3, which only makes sense in terms of the graph, right?
I'm trying to find the result. Okay. Let me just point out that, I mean, these rings that we get here, of course, if R is a field, they will be graded for Neumann regular and so on. I guess if R is just prime, then it doesn't have to be. It doesn't have to be for Neumann regular. So yeah.
Okay. One more thing. When you cited this result of Royer and someone else, that describes the Leavitt path algebra as a cross product, and you describe the algebra D of X, which appears there as a partial cross product.
This is all right. Let me see if I remember this.
I mean, you mentioned infinite paths and paths ending in sinks, and I thought maybe he is assuming that the graph does not have infinite emitters, because I mean the paths that end in sinks and the infinite paths are some of the elements of the space, the canonical space associated to a graph, right? And the other elements are those ending in infinite emitters. Since they were not mentioned here, I thought perhaps you were assuming that it had not.
I understand. I understand the question. So let me first just say that I only included this as a little bit of context to show that there are different gradings here coming from different ways. So I'm not really using this in any part.
No, of course not.
Yeah.
But I know there is such a result, but I'm not familiar with the particularities.
Yeah, I have to be honest here. I don't really remember, but I don't think that row finiteness is assumed here. So I think that this holds for any graph, but
it's
definitely sure about this.
Definitely not assumed to be row finite.
But in the definition of the X, do paths ending in infinite emitters need to be included or not?
I think so.
Yeah, I can't say.
Okay. That's all on my part.
This is a very complicated space, which I think the first instance of that space appeared in my paper with Marcelo Laca on Kunstkrieger algebras for infinite matrices. So it's the path that end in there's a mixture of finite path and infinite path. So this is a quite involving space to work with. But I also had another question, and the question was, now that you characterize prime algebras, do you think there's any hope of characterizing all of the prime ideals inside of a Leavitt path algebra? Because if you're dealing with C-star algebras, then there's the Abrams-Bell-Rangaswamy conjecture, which has been proved for this kind of algebras, and so what you get is there is a way to list all of the primitive ideas, but for separable C-star algebras, primitive is the same as prime. So there is, in the C-star algebra case, I think it's possible to describe, or at least to list all of the primitive ideas. So I think it's high time that maybe somebody could classify those primitive ideas, those prime ideas on a Leavitt path algebra. I think there's hope for that.
That's an interesting question. I have to admit we haven't at all thought about that yet. So, and I cannot really say if any of these techniques are useful for that.
Oh, I think they are. They definitely are. There's this paper that I wrote with Misha Dokushayev on the Abrams-Bell-Rangaswamy conjecture for partial cross products, and there we didn't go too far, but we got some ways. So the proposal is to take first of all the second grading that you discussed. I think it's much more relevant to studying the prime ideas of the algebra, because the algebra SE is commutative. Right, and so when the algebra SE is commutative, then then according to the Abrams-Bell-Rangaswamy conjecture, which is proven for nuclear algebras, you look at the group algebras you have to induce ideas from the stabilizer subgroups of every point back to the algebra. And the theorem says that every primitive ideal, which is the same as prime ideal, is induced from a primitive ideal on one of those group algebras for the isotropy group. So I think that would be the way to think about this question.
No, thank you. We will look into this.
Okay, let me know if you have any luck.
Hey, absolutely.
Your microphone is muted, Guillermo.
So if there are no, thank you. If there are no more questions, I will stop the recording now.